Okay, in this video we'll begin our study of probability by looking at a few introductory examples. And the first one here, if you roll a fair die, what's the probability that you will get a number bigger than 2? So when we see the word die in probability, it typically refers to a six-sided cubical die like this one here. And if it's a fair die, we're assuming that any of the, all of the six sides are equally likely to turn up. So it's one side is not more likely than any of the others. So we don't have a weighted die or anything tricky or dishonest like that. So what's the probability that you get a number bigger than 2? So that, being interested in numbers bigger than 2 is something that's called an event in probability. So we're interested in an event A that's only getting a number bigger than 2. So we could work with probably the easiest definition of probability, that the probability of this event A getting a number bigger than 2 would be the number of favorable outcomes, the outcomes that we are interested in getting, divided by the number of all possible outcomes. So of course, if we recognize this is a six-sided die and the faces are numbered 1 through 6, we can list off and all 6 numbers here. And incidentally, this is referred to as the sample space. Once you list all your possible outcomes, and this is a pretty small sample space. And the number of favorable outcomes are, of course, the numbers that are interested in, the ones that are bigger than 2. So that would be 3, 4, 5, and 6. So following this user-friendly definition of probability, the probability of this event A getting a number bigger than 2 is going to be any of those 4 numbers, 3, 4, 5, and 6, turning up as being a favorable outcome or an outcome we're interested in, divided by the total number of outcomes, which of course are the numbers 1 through 6. So we could reduce this fraction. 4/6 is fine. We could also say it's 2/3. We could write it as a decimal, which is a little less than ideal because we'd be getting into some rounding error here. But we could say it's roughly 0.6667, and we could also express it as a percent by timesing that by 100, 66.67%. So there's the probability that we're interested in. Now, a little more mathematically rigorous approach to determining a probability is to use set notation, and we got pretty close to actually using set notation. So this event A is actually a number of outcomes that can be written as a set, and the sample space in itself is a set. So that would bring us back to using set notation. So let's leave a little bit of space here and recognize that this is, the more mathematically rigorous definition of probability, where you start seeing set notation and actually the cardinality or the number of elements listed there that are each of these sets. So U typically means the sample space. So let's list that first. So the sample space in this experiment of rolling a die, the total number of possible outcomes are still the numbers 1, 2, 3, 4, 5, and 6. And the outcomes that we're interested in, that defines our event A. And of course, that event A is really just a set of outcomes that we're interested in. And those are the outcomes bigger than 2. So 3, 4, 5, and 6. So remember, we have 2 sets here. A is a subset of U, the universal set. And we're not interested in just dividing sets because that doesn't make any sense, which is why we have to count the number of elements in each set, which is why you see that N in front of the brackets in each of those set names there, A and U. So the probability of this event A is the number of elements in the subset A, which of course is the number of numbers in A, which is 4, divided by the number of elements in the universal set or the sample space. That of course is 4/6. Which, just like before, we could reduce it, write it as a decimal, 6667, or write it as a percent. So it's not necessarily better to use set notation. Just be aware that if you see somebody writing down set notation and counting elements in a set, it's the same thing as we did initially by just looking at the total number of outcomes and I guess marking off the favorable outcomes and counting them up as well. And incidentally, I guess before we move on here too, I guess it's important to understand that a probability of any event, of course, has to be somewhere in between. We'll say probability of A has to be less than or equal to 100%. Can't be more than 100%. And it's probably not going to be negative either. You shouldn't have any negative percents of, probabilities, of course, because that doesn't make any sense. You can have negative percents, I guess, in other contexts, but not in probability. That would mean if we're thinking decimals, which we probably should be, a little more rigorous, probability of A has to be between 0 and 1. Okay, in our next example here, we're going to look at a standard 52 card deck, and we're going to choose a single card from a standard deck. We're trying to figure out what's the probability that you will get a red face card. So going back to our user-friendly definition again, so the probability of a certain event, which in this case now is not getting a number bigger than 2, but getting a red face card, we'd have to figure out what the total number of possibilities are. So if it's a 52 card deck, we're only picking one card out, so of course we could pick any of those 52 cards. And the outcomes we're interested in this event A are only the red face cards. So if we know what a deck looks like, this will be helpful. And for those of you who are card sharks, you have an unfair advantage, I guess, right now. But anyway, here's a standard 52 card deck. And you can see there's 4 suits, 2 red suits, and 2 black suits. And the 2 red suits are diamonds and hearts. And of course, the 2 black suits are spades and clubs. So if we're interested in face cards, I know it says red, but just keep in mind there's 3 face cards in each of the 4 suits. So there's 12 face cards in total. And if we're interested in only red face cards, that would narrow that down to 6 red face cards. A Jack, Queen, and King in hearts, and a Jack, Queen, and King in diamonds. So our number of favorable outcomes, of course, is just going to be 6. So that is that for that probability. Now, I guess we could tinker around with set notation and stuff, but then we'd have to start writing out all 52 cards in a universal set and then figure out a way, I guess, of just drawing out hearts and diamonds for our face cards, and that would be quite time consuming and rather a colossal waste of our time. So let's just go with the number of favorable outcomes, the ones we're interested in, divided by the total number of outcomes, and we have our probability. And I guess incidentally, if you want to divide that and reduce it, divide top and bottom by 2, I guess, we could write this as 3 over 26, just to be aware that if you have 6 over 52 and you check an answer key, it's quite common that we reduce fractions. Not saying you need to, but just, of course, clue in that both of those fractions are the same and your answer is actually correct. Okay, in our last example, we're going to look at rolling a pair of dice. So not 1, but 2 dice, of course. So if you roll a pair of dice, what's the probability that you will get a sum equal to 10? So we're adding the 2 faces together that turn up, and we're looking for a sum specifically of 10. So we could list our entire sample space, and we'll actually do that in a few more moments because this is a pretty common question type. So it's good to know what your sample space consists of. But before we do that, let's see if we can count our total number of outcomes. So what are the total number of outcomes if you roll a die twice, or in this case, if you roll actual 2 dice, a pair? Well, we can use our fundamental counting principle to predict how many outcomes we would have, because we could have any of the 6 sides turn up on the first die, and we could have any of the 6 sides turn up on the second die, which would mean, yep, we have 6 times 6, 36 possible outcomes if we roll a pair of dice. Now, we got to keep in mind that it's not going to be 36 unique sums, so we still have to figure out how many different ways we can get a sum of 10. So let's see if we can figure that out before we go ahead and, I guess, piece our probability together. So how many ways can we get a sum of 10? Well, maybe we'll look at it as just listing a face that could turn up on the first die and a face that can turn up on the second die. And if we keep the numbers 1 through 6 in mind, well, how can we get a sum of 10? Well, of course, we could have 5 on each of the die. There's only one way that can happen. I could have a 4 on the first die and a 6 on the second. Or I could have a 6 on the first die and a 4 on the second, and that feels like I've just written out the same outcome twice, but it's actually 2 different outcomes there, because just keep track of the faces on the first die. The faces have changed. It's 4 to 6, and then it's 6 to 4, so those are actually unique outcomes. And of course, there's no other ones, because if we start considering 3 and 7, well, we've gone past our 6 possible faces, so that would mean there's 3 outcomes of interest here in this event of getting a sum of 10, or we'll just say 3 favorable fave outcomes. So that's more than enough. We can actually put together a probability now. So the probability of this event A, remember this event, we're interested in the outcomes where we get a sum of 10. So we have to keep in mind there's 36 possible outcomes that could happen if we roll a pair of dice, and of those 36 we just did a little listing there, and we figured out there's 3 favorable outcomes that would give us a sum of 10: 5 and 5, 4 and 6, or 6 and 4. So of course we can reduce that down to 1/12 if we wish. It's not completely necessary. So that's one way of calculating this probability, and something that we will definitely want to do when our sample space gets a little bit out of hand. We don't want to have to start listing off hundreds or thousands of outcomes, and then some sample spaces are actually infinite, so listing them is not an option. So let's see for this sample space, since there's only 36 outcomes, a nice way of, listing them and organizing them and starting to maybe see some patterns in this sample space as well. Okay, so here's one way you can keep track of your sample space when you roll a pair of dice. And you can see I have my 2 die color-coded, but most importantly, I'm just keeping track of the 6 faces on die 1 and the 6 faces of die number 2, and they become row and column headers. And of course, if you follow a red and blue number, you will see that outcome, and there's going to be 6 times 6, 36 possible outcomes. Of course, it's our fundamental counting principle. Just a graphical organizer for that fundamental counting principle, which is a lot more useful than a tree diagram, because if you have a grid here of these 36 numbers, it keeps track of our sums quite nicely as well. And you can start to see that there's only one way we can get a sum of 2, a pair of 1s, but we can see there's now 2 ways we can get a sum of 3. So if we follow these diagonals on our grid, you can start to see all your possible sums. And you can see the sums get more and more likely the closer we get to that longest diagonal. So now we have 3 possible sums of 4, 4 possible sums of 5, 5 possible sums of 6. And here's the most likely sum you can get when you roll a pair of dice. There's 6 different ways you can get a sum of 7. And now our sums become a little less likely. There's only 5 ways you can get a sum of 8, 4 ways you can get a sum of 9, and there's 3 sums of 10. As you know, we counted that. Just kind of guess it wasn't as pretty as this, but we just listed the possible outcomes and figured out that there was 3 ways to get a sum of 10. But if you have your sample space in front of you, you just have to glance at this diagonal and count up the 3 possible outcomes, which might be a little faster, assuming you already have this grid somewhere in your notes or on a piece of paper. And to finish off our sums, there's only 2 ways to get a sum of 11, and our biggest and again least likely sum, at least tied with the sum of 2, is our sum of 12. So that shows you that there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible sums that we can have when we roll a pair of dice, and some are much more likely than others. The winner is the sum of 7, which has a probability of 6 out of 36, and the least likely sums, as I mentioned, are the sums of 2 and 12, which is only going to happen 1 out of 36 as a probability. Okay, that rounds out our introduction to probability, and keep in mind that if you're looking for the probability of any event, it's always defined as the number of favorable outcomes divided by the number of all possible outcomes. If you choose to use set notation, I think if your sample size is small, set notation might actually be helpful, but as long as you can visualize, if not write down your sample space when it's manageable, it should make calculating probabilities pretty easy. And one thing to keep in mind with these 3 examples in this video, our events were pretty basic. These were, I guess, just an individual event in each of these problems, or a single event in each of these problems. A single roll of a die, a single, I guess, a selection of a card from a full deck, or a single roll of a pair of dice. In future videos, we'll start chaining multiple events together, and that's where things will become a little bit more interesting, and we'll have to probably rely more and more on our accounting chops, because as our sample size grows, writing out the entire sample space becomes a less and less viable option.